Okay. Okay, so first of all, let me make a correction in yesterday one statement which I made. So I made the following lemma that let be a norm defined on a vector space V and B is equal to those x belongs to V such that norm x less than equal to 1, then is an algebra norm if and only if B into B is equal to B. Okay. There is a small issue here. I should add here and 1 belongs to B. A priori, I don't see, at least I could not see that that B into B is equal to B will imply immediately that 1 belongs to B. Norm of 1 star, you can say that if norm of Fg less than equal to norm F into norm G, because what is the definition of an algebra norm? Not just that the norm of Fg less than equal to norm F into norm G, norm of 1 star also, norm of 1 also should be 1. Sorry, I should not, no star. Norm of 1 also should be equal to 1. And the condition that B into B is equal to B will imply that norm of F into G is less than equal to norm F into norm G. But this one also, the norm of 1 is equal to 1, as such it may not imply. It will imply that norm of 1 is a norm of F into G less than equal to norm F into norm G may not imply that norm of 1 is equal to 1.
What is 1 in V? What is 1?
Okay, it is okay. So it should be an algebra. Of course, how can I talk about an algebra norm without having an algebra? If there is no multiplication, I cannot talk about norm F into G. So you have a R algebra or C algebra. Okay, thanks. So, okay, so, and probably it is easy to, anyway, it is easy to probably construct examples where this is satisfied but this may not hold, because for instance, if I just multiply some scalar by 2 times norm F infinity, then probably it will be a still a norm. It will satisfy norm F. I mean, what I'm saying that 2 times norm infinity, it will be still a norm, isn't it? And it will be an algebra norm, but the norm of 1 is not 1, it is 2. Okay. Another, okay, so we have to, so this one belongs to B, we have to add. Another remark which I was earlier saying that because our dual will be an algebra norm and our original norm may not be an algebra norm. So I wanted to, in our applications, the dual of a cut norm is an algebra norm, and then I was saying that that does not mean that the cut norm itself may not be an algebra norm. So example of a norm such that its dual is an algebra norm, but norm is this is not algebra norm. For this, I guess you can just take L1 norm. L1 norm as such is not an algebra norm. Summation mod f g is not less than equal to summation mod f into summation mod g. Is it? Means with the, but L infinity norm is definitely an algebra norm. Anyway, if I am hidden. But L infinity, but its dual, which is an L infinity norm, is definitely an algebra norm. Here the multiplication is pointwise multiplication and not the convolution. Okay. So now in order for, if that is the case, then in order for me to verify that the cut norm is an algebra norm, I also need to verify that the one belongs to this convex hull which I took. So, but for that, so what was this basic functions? They were given A1 subset of Z mod Pz to the power r minus 1. A1 AR subset of Z mod Pz to the power r minus 1. The basic functions was this which was this x1 xr belongs to Z mod Pz such that x1 plus xr is equal to 0. IAR x minus r. So now, okay, so this was the basic functions. So now if I just take all this AIs to be equal to Z mod Pz to the power r minus 1 itself. If I take all this AIs to be Z mod Pz to the power r minus 1, what will be the convolution? This value will be always 1. So then, in that case, this function so the function 1 is there in the convex hull of the functions because it itself can be written as this basic functions. All right. Another thing, the lemma which we will require in order to show that this. So what we did, we took defined the cut norm, we took these functions, negative of these functions, and took the convex hull of this set, forms by these basic functions and their negatives. Okay, and then we wanted to prove that the unit ball is equal to the unit ball with respect to the dual norm is exactly equal to the this convex hull. So for this, first of all, we showed that this supremum over phi belongs to this k. K is, I am calling this convex hull of this basic functions and their negatives. Okay. All right. And since in fact this k is symmetric, I need not take this modulus. I can just take f phi. There is no need for me to take the modulus because I can just take, because this k is symmetric, k is equal to minus k. This means I call this phi r. Okay. All right. So this phi r had a property that phi r is equal to minus of phi r, and 0 belongs to phi r. All right. Okay. So now in order to prove that the norm with the unit ball with respect to a dual norm is exactly equal to this phi r, one can show a general result that let k be a convex set minus k is equal to k. Okay. And of course, if minus k is equal to k and k is a convex set, then 0 also will belong to k. I need not add it. Okay. And suppose the norm of some norm, we have defined some norm and it is given by supremum over phi belongs to k. Okay. So this means in general, for the general convex set, it may not define a norm. But suppose our norm is given by this. Because our convex set may lie in a smaller dimension. And so inner product f, I mean phi is 0 may not imply f is equal to 0. For instance, if in R2, if I just take a point, this is a 0 point, means or any point in the one dimension, then that is a convex set, but there are so many functions whose inner product with that is 0. So therefore, it may in general not define a norm, but suppose it defines a norm. Then if B is equal to those, x belongs to V, such that phi star is equal to 1, is less than equal to 1, let B is equal to this, then B is equal to K. Okay. All right. All right. So, okay, I will, K contained in B, I will leave it for you to verify exercise. Sorry.
Follow K will be unique.
I mean,
In our case, we have this.
K, I mean, so yeah, I mean, what you are saying that if I take a,
K has to be B.
K has to be a unique, I mean, you cannot have a, I mean, so but if I am saying that this is exactly the unit ball, you cannot have a unit ball is unique. So you cannot take a bigger or a smaller set and when the set is convex. And then this will not be same. That's a part of the, so that is a part which I am now saying in essentially that, which says that this is unique. So suppose phi does not belong to K, is less than equal to 1. Suppose there exists such a phi which does not belong to K, because I am now trying to say that B is contained in K. If not, then there will exist phi which does not belong to K and norm of phi star is less than equal. Then by Hahn-Banach separation theorem, there exists F such that is greater than 1 and less than equal to 1 for all phi in K. Okay? So, but then, but this fact, the fact that this F with phi for all is less than equal to 1, this implies norm of F is less than equal to 1. Because that is the definition of a norm. It's a supremum over all the functions. By our assumption, the norm is given by supremum of F with phi for all overall phi in K. And if it is less than equal to 1 for everything, then it is supremum is less than equal to 1. So therefore, this implies norm F is less than equal to 1. All right? But on the other hand, F phi by the definition of a dual norm, this is less than equal to norm f into the dual norm. Which is less than, because norm of f is less than equal to 1, this is less than equal to the dual norm of phi, or psi. But on the other hand, this is greater than 1. So norm of phi star is greater than 1. But our assumption was that norm of phi star is less than equal to 1. So that is a contradiction. So because we have shown that this norm f is given by the supremum over phi belongs to this convex set f phi, that and our convex set is symmetric, our convex set contains 0. Therefore, it immediately implies, using this lemma, that indeed this convex set is the unit ball with respect to dual. Okay. Symmetricity is used here, that norm f is equal to supremum over this. Generally, I should write modulus, but I need not write modulus because it is symmetric. If it is negative, you just take the minus of phi, and that will be positive. So norm of f, because it is symmetric, the supremum will never be negative quantity. Supremum will always be a positive quantity. Because if it is negative, just take the minus of that, and that will become a positive. Without having the symmetricity, I cannot say that the supremum is a non-negative quantity. So I have shown all the steps involved in the proof of proving that the dual norm of the cut norm is a algebra norm, except that the fact that this phi r is closed under multiplication. In order to show that the phi r is closed under multiplication, it is enough for me to show that these basic functions, their product can be written as a convex combinations of the basic functions. Product of two basic functions, IA1, IAR convolution and IB1, BR convolution, that can be written as a convex linear combinations of the basic functions, and that I will leave it for you to verify from the notes. So what is the paper I am mentioning is this Conlon, Fox, Zhao, Green Tau exposition. Okay, so this is what we have shown. This decomposition theorem is theorem 5.1. Okay.
We see that when we are seeing supremum, that set will be bounded above to get the natural upper bound.
why the supremum will exist. You're in a finite dimension, no? There are only finitely many sets, basic sets. And the convex combinations, although it is infinite, but on the other hand, once you have a bound on the supremum over the basic sets, the same bound will hold for the convex combinations also. All right. So now, okay. So, but now what is this V business? We have shown the decomposition theorem in an abstract setting. First, that for any function given eta delta greater than 0, there exists an epsilon, such that for any function f from z mod pz to r, for which there exists this new function which dominates your f and whose norm v minus 1 is less than epsilon, and norm of L1 norm of V1 is at most 1, then we can write down this f as a function f1 whose L infinity norm is not too large, as well as the plus f2 whose norm is small, provided that the dual norm is an algebra norm. But in our application, when we talk about these primes, then we have to say that our primes are dominated by this pseudo-random measure. So what is this pseudo-random measure, first of all? In order for me to say that, so now I will, okay. So for the next part of this lecture, I will be telling a certain number of things without giving details of any of them. Okay? I will only point out the salient features involved in them. For the particular reason that the details, though not very difficult, are somewhat messy. So I will just restrict myself. So there will be a lot of hand waving, and you have to trust me that this thing works. I will only point out the main idea involved in the things. So before so I have to talk about the pseudo-random measure, but before talking about the pseudo-random measure, let me motivate the pseudo-random measure. Okay? So for that, let me motivate. So we had defined this gamma kf Yeah. All right. So now if, okay, for suppose A is a subset of Z mod Pz with cardinality A is equal to alpha P. Yeah, okay. Maybe uh, for a single function I had defined, let me okay. So, so cardinality A is equal to alpha P. So, so therefore gamma K A here A is denoting the indicator function of the set A. Okay. Now what I do is that I subtract alpha and add alpha in each one of them. Okay. So then when I expand it, there will be one term which will be equal to alpha to the k, 1, and then there will be other terms. So let me define now for the general, not just for single function, gamma k f1 fk to be equal to okay. So the other terms will involve gamma k f1 fk first, and where the fi's will be equal to either ax minus alpha or equal to alpha. There will be various terms of this type when you expand it out. But except this term, in each one of them, one of the fi's should be equal to ax minus alpha. All right? Now, if I can show under certain conditions that the contributions coming from each one of them is much smaller than the contribution coming from this term, then I have obtained a lower bound for gamma k A. Yeah. So now the question is, how do I obtain a upper bound for this particular quantity when, okay, gamma k f1 fk, where either one of the fi's is equal to ax minus alpha. So in particular, generally, how do I obtain? Okay. So let us restrict ourselves to simpler case for the notational things that we just restrict ourselves to gamma k, 1k is equal to just 3. All right. I will, okay. Now I will reparameterize this thing in the following manner. I will say that this is equal to okay. This idea of reparameterization is probably coming from graph theory. So let me just quickly tell you this. So of course you have to verify that these two things are same. I am not doing it. But let me tell you that what exactly is going. So X, so you have a tripartite graph. Okay. So you join this and this here edge if 2x plus y belongs to A. Join this two by an edge, y and z में क्या था? Minus y minus 2z belongs to it. And here x minus z belongs to it. Okay. So suppose there is a triangle. So you have joined these two things. Suppose there is a triangle. There exists a triangle in this graph. So first of all, the graph is clear. Suppose there exists a triangle in this graph. Yeah, A is a subset of Z mod PZ. Fixing a subset, we have defined a graph. So graph depends upon the A subset of Z. Like a Kelly graph. Except in the Kelly graph, you take x minus y belongs to A, but here. Suppose there exists a triangle in this graph, then this means what? That 2x plus y, there exists a, that means there exists a x, y, z such that two x plus y, x minus z, and minus y minus 2z, they are contained in A. But this is an arithmetic progression. This thing is an arithmetic progression with common difference minus x minus y minus z. So in other words, your subset contains an arithmetic progression if it contains a triangle. But you want a okay? Of course, there are trivial triangles here. The trivial triangles correspond to the fact that this x plus y plus z is equal to 0. So if A does not contain any non-trivial arithmetic progression, that means what? That each of the edge, that means the only triangles correspond to x plus y plus z is equal to 0. So if x and y are connected to by an edge, by a particular edge, then the only triangle this edge can be a part of it is already given, because this edge determines this two endpoints x, y, and since x plus y is equal to z is equal to 0, the z is also determined. Then each edge is contained in a unique triangle. Okay. Now, how many edges are there? So given x, if you fix an x, there exactly you want 2x plus, suppose I can assume that 2 is co-prime to my z. So I mean 2x plus y should be there in A. That means y is equal to minus 2x. I mean y belongs to minus 2x plus A. Okay. X plus 2y belongs to 2x, yeah. Y belongs to minus 2x plus A. So there are exactly cardinality A many possibilities. So therefore 3n cardinality A many edges. For each of this point there are exactly cardinality A many things. So there are 3n points, so 3n times cardinality A many. How many edges a particular point can be a part of it? There are cardinality A many edges. coming out from the each vertex. There are 3n vertices, so therefore 3n times mod a number of edges. There are repetitions. Each edge will be counted twice, so okay, 3n by 2 maybe.
In this P,
Yeah, sorry, P. Okay. And since each edge can be contained is contained in a unique triangle, the number of triangles in this graph is at the most the number of edges. So 3p times cardinal T, a many things. So number of triangles are at the most O of p square. So definitely little o of n cube. Now Ruza and Zameredi, they proved that if a graph G contains little o of n cube, G is a graph on n vertices and contains little o of n cube many triangles, then we can remove little o of n square edges to make it triangle free. Okay. And then using this result, the Ross theorem follows immediately. Okay. Anyway, so this reparameterization probably, I mean, so that it is easy, it follows from this particular thing. Because there is this 2x plus y minus 2z and this business. But what is this reparameterization doing for us? Why is it important?
complete graph will have n choose 3 triangles,
Yes.
which is O n cube.
N choose 3 will be about n cube only. There you cannot remove. So that is not little o of n cube. I mean, divided by n cube is going to 0.
But here n is fixed or you are varying it.
So here, of course, it's for sufficiently large p. It is always, that is the assertion, for sufficiently large p. P is fixed but not fixed. Okay. So what is this reparameterization doing for us? One thing this reparameterization is doing is that there are 3 variables and none of this linear form depends on all 3. Neither this thing depends, this one does not depend upon z, this one does not depend upon y, and this one does not depend upon x. So I can use Cauchy-Schwarz to get rid of the other functions. So, because in the things which I wrote, there will be one function a minus alpha. So I will have some information about a minus alpha, but I won't have information about a. So I want to get rid of the part which contains a. So suppose I want to bound this thing in terms of the F1 only. Okay, then I will do it, and suppose we want to obtain upper bound for this. In terms of F1, and suppose under the assumption, we will assume a big assumption which will not be satisfied in the primes case, is that all these Fi's are less than equal to 1. But let us see how to get rid of the other functions. The way how usually one gets rid of the other functions in this topic. So first I write the things with respect to what are the functions? Okay, so I will get rid of F3 first. Okay, so I write down this because since F3 does not depend upon x, it will come out. So now this is less than equal to E z v y this thing. But since I have assumed that my F3 is bounded by 1, I can erase this. And now use Cauchy-Schwarz to say that this is less than equal to E z y, because I don't like modulus to be inside. I would like to again expand it. If it is a square, then I can expand it. If it is just a modulus, I cannot expand it. So I use Cauchy-Schwarz to obtain this. So now what it has become E z y, E x1, x2, f2 x1 minus z, then what? F2, F1 to x2 plus y, F2 to x2 minus z. Sorry? 2x2 minus z, no? Oh, sorry, x2 minus z. x2 minus z. Since I am assuming real valued functions, I need not take a bar, otherwise I need to take bar. So now I can, now I want to get rid of this F2 also. So what I should do this EX1. What did I do? The F2 I want to get rid of this thing, so X1 and X2 should come out. And Z also should come out. And Y can remain inside. All right. So now when I, okay, now I can again apply this Cauchy-Schwarz. First of all, I apply just this, that this quantity is less than equal to the modulus of this function, and now it involves only the F1 thing, and F2 and F3 have gotten we have got rid of. But I still don't like this modular sign inside, because I cannot still interchange the summations and things like that. So I will again apply things to all right. So now if you, okay, I will define this Gauss norm. So now when you see this such elementary algebraic manipulation, and once you know what is the definition of a Gauss norm, then this is exactly the Gauss U2 Gauss norm of a function f. Why I did this? Because if you observe this expression, then you will expect that now in our cases, our Fi's are not bounded. When we are talking in the primes, there is this lock, I mean the inverse of the density which comes above. So it is not, the norm Fi's are less than equal to the inverse of the density of the primes inside integers. So therefore, it is not really a bounded function. So we cannot go through this Cauchy-Schwarz business, because there is, I can no longer here erase this F3, because F3 is unbounded. But on the other hand, you will expect, you will expect that even if F3 is not bounded, this quantity is involving the averages. So if even if the my functions are not bounded by bounded by a function whose average in some sense is small, in what sense I have to define it, then probably still this kind of things I can perform and be done with it. Because you don't really need this, I mean, your expression which you are trying to bound is an average of certain things. So if the individual, you don't really need the L infinity norm to be bounded, but certain, what you need is that f should be bounded by a certain function whose average in some sense is bounded. All right. Yeah? Timer did not work. Okay. No, okay. So now, of course, I mean, I am oversimplifying this. So I will tomorrow then. Oh, I don't have much time left. Okay, so I will see what I can do tomorrow. I have not yet decided. Okay.